Hi everyone, in this video we're going to be in Module 3 and we're going to be looking at the standard deviation and two ways that we're going to be measuring unusual. And by that I mean, what does it mean to be an unusual statistic? So far you've been looking at statistics, comparing them to chance models and saying either it's usual or unusual. We are going to put some more concrete math and just concrete ways to make that decision. So, the first thing we should talk about is the standard deviation. So the standard deviation is a measure of the spread of a set of numbers. Okay? So we're not going to do this calculation. There's a formula for it, but we're not going to go through it. We'll have a computer do it when we want to, but you probably have a calculator that can do it as well. But what we want to do is understand what it means. So the first thing we have to talk about is the standard deviation is a number. It measures spread. And there are two important things. The first is if your standard deviation is large, and we'll talk about what large looks like, but if it's large, that means your numbers are more spread out. So the larger the number, the more spread out your data is. A smaller standard deviation, on the other hand, means that your numbers are less spread out, tighter together. So this is really important for us to learn about so that we can understand how to describe possibly a large set of numbers by only looking at two things. And so far we've looked at the mean or average. So far we've gone, okay, here's the mean, that's the middle, that helps me learn about this set of numbers. And you guys have done a good job with that with quantitative data. But there's also the standard deviation, because knowing just where the middle is not enough. You also want to understand how your data is spread out. All right, so let's consider the following example. So in this example, I've got two classes and they take the same quiz. So each class has a mean or average of 7. So each class has an average of 7 on the quiz. Okay, so 70%, that's a C. If this is the only number we use to understand the class scores, we would say they're the same. I come up to you, Class A, Class B, they both got 70% average, and you would say, okay, and in your mind, those scores are the same, because that's the only piece of information I've given you. But there is an option to look at the standard deviation, and that can be very telling. So for example, Class A had the following scores. 1, 1, 1, so 3 people got a 1 out of 10, someone got a 7, and then 6 people got a 10 out of 10. That is quite a spread of scores. And what I've done down here is I've tried to give you a nice little visualization of that, right? Here are your people who got a 1. Here are the people who got a 7. And these are all the people who ended up with a 10. So if I just told you the average was a 70, you might have made some assumptions. I bet based on this class so far, you would have assumed some people got a 70, some people got a little higher, some people got a little lower. In reality, though, 3 people got a 1 out of 10, and that was probably for putting their name. So that tells me, and I want you to put yourself in the teacher's point of view here, right? If these are your scores, that tells you 3 people really need a lot of help. They don't know what's going on. 1 person is pretty good, you know, they got some stuff to clean up, but okay, 70 is not bad. And then there are 6 people who got a perfect score, and they really seem like they know what's going on right now. So that information of how the scores are spread is valuable for you to have, not just the middle. In this case, the middle doesn't really tell you anything. In Class B, though, every single student got a 7 out of 10 on the quiz. And so there is actually no spread here. And to be specific about this, in this scenario, the standard deviation would actually be equal to 0. So that will only happen if there is literally no spread in your data points. So Class B is extremely consistent. They have a small standard deviation. Class A overall is inconsistent in terms of just looking at everyone's score. They have a lot of spread. So this would be a higher standard deviation. So it's valuable to be able to look at some data, go, where's the middle? That's an important number, but also be able to go, well, how is the data spread out? Because that's valuable information to have, and that'll be valuable for us moving forward. But that's the idea. It's just the spread. If your data is very close together, lots of people getting very similar scores on the quiz or heights or whatever, then you have a small standard deviation. Okay? If you've got people who kind of are all spread out, you've got a lot of people who are 7 feet, people who are 4'11", people in the middle, then you've got a higher standard deviation, more spread. Okay, so that's standard deviation, just describes spread. The key thing that you need to be just paying attention to, this is the key thing right here, key idea. Bigger number, more spread. Smaller number, less spread. Okay, so I also promised you, finally, us talking about how we are going to call a statistic usual or unusual. So, just to remind you again, what are we talking about here, right? Well, if I have a chance model, what you've done so far is you've taken a sample that you've taken or was in a problem, you've gotten the statistic, Buzz and Doris 15 out of 16, we're about to use that one, just as an example to remind you. You took that number and compared it to the chance model. If that number does not fit the model, you were saying it was unusual and then making a conclusion. Okay, that's what we were doing last week. So here are 2 ways we're going to use to actually do a calculation to tell us usual versus unusual. No more guessing. So the first one is called the p-value. So the p-value, we just talked a little bit about last week on your Module 2 sheet, just right at the end, a little piece about it. But this is where I'm actually just first time really introducing it. So the p-value is what you've already pretty much done in your heads. So I'm just going to go back through the Buzz and Doris example, and when the p-value pops up with what we've already done, I'll make a comment. So let's remind ourselves, Buzz and Doris, 15 out of 16. Right? So 15 out of 16 was their statistic. So what did we do? We said, okay, we're going to make a chance model based on a coin flip or 50-50. So remember, what did we say? We said, okay, well, Buzz and Doris are communicating, which is great. We want to, that's a possibility. Or they're not communicating. Well, if they're not, then Buzz has a 50% chance of getting the right thing. So once we held on to that, we said, okay, let's focus on that. What should it look like to do 16 simulations, 16 coin flips? What should it look like for Buzz and Doris to do their experiment 16 times if they're really just guessing? What should actually happen? And so that's what the chance model is. So we'll start with this one right here. So this chance model is what it's supposed to look like if you do 16 coin flips, 16 processes that are 50-50. And what this is we've done it many, many, many times. So remember, sometimes you get 8 out of 16. That's good, right? That's about 50%. That's kind of what we're thinking. Sometimes you get a little more, 9, 10, not too bad. Sometimes you get less, 7, 6. Okay, that's all fine. But we were asking about 15. And remember, 15 is not on the picture. Never even comes up on the picture. And so what you were saying before was, okay, it's not even close to any of the other dots. We're going to say that's unusual. Okay, so here's where the p-value comes in. The p-value says this. So the p-value says count the dots. Remember, each dot is a simulation of the 16 coin tosses. So count the dots at your statistic or more extreme. And so visually, what that looks like is find 15 out of 16 and then count all the dots at this line or to the right in this scenario. More extreme means further from the middle, okay? And what happened there? Well, there were no dots. No dots at all out of the 1,000 that happened with. And we divide by the total number of dots in our picture. So the p-value is count the dots at your statistic or more extreme, and then divide by the total. So this would be the total dots here. So we're going to count the number of dots, that's a 0, and we're going to divide by the total. This number is going to be how we measure your being unusual. And so specifically, we are trying to define here, be very specific about this, the p-value is the probability, so there's that word probability coming back for us, probability of getting our statistic. So in this case, remember, we're thinking the 15 out of 16 or more extreme if, this is a big if, the null is correct. Okay, so this is another classic example in this class of you've already done this idea a bunch of times. I'm just putting a name on it. You've already assumed the null was correct. Remember, in this case, what is this, right? So this would be 0, that's the p-value, is the probability of Buzz and Doris getting 15 out of 16 correct if they are just guessing. All right, so let's think about this. This is what you thought the whole time. When I told you 15 out of 16, or when you read it the first time, you said, no way. No way they're not communicating. 15 out of 16, no way you're going to get that. That's all we're doing here. We're trying to put an actual number on it. We're saying, well, you know, your intuition's good, but let's think about this. What is the chance that that could happen? And I have to put a little caveat here because this actually isn't totally correct. This is an approximation. So squiggly equal signs means, well, not quite. That's why it's squiggly. It's very unsure of itself. So it's not technically 0, and we would need calculus to be able to actually do this calculation. Or in other statistics classes, there are these giant tables of values that people have calculated for you that we could just look up. But instead of that, we are going to run these simulations, and we are going to approximate the probability, the p-value. So we're never actually getting the 100% true p-value. We're approximating it. But it's so close with these simulations that it doesn't matter. So just a little caveat. We got to use little squigglies. We're going to say p-value equals, but just for the first time, you should know it's not exactly the p-value or exactly the probability. But let's go back to this. The probability of Buzz and Doris getting 15 out of 16 correct if they're just guessing. That's what we already thought. And what we're saying is it's basically 0. There's basically a 0% chance of that happening. Okay, so what happens? If your p-value is that small and your probability of randomly getting 15 out of 16, you're saying that's super small, then what should we do? We should throw out our null hypothesis, which we've already done together. So the p-value is this great example, again, of you've already done this idea. Take your null hypothesis from last week. Make a chance model out of it. Compare your statistic. If your statistic seems unlikely or unusual to happen under this chance model, we go, let's throw out our null hypothesis. I don't think that that's right. This is how we measure it specifically. The p-value tells us that probability specifically. So you don't have to look at a picture and kind of think, well, it's kind of the border. Nope. We'll do this proportion, count the dots divided by the total dots, and that'll give us a number, and then we'll have guidelines for it. That's it. So what's the other way we kind of think about doing this? So that's p-value. The other way is called the standardized statistic, and there's the z-score and the t-score. So let's forget about that for a second. Okay, so then the standardized statistic is another way you might already kind of think about this. And the other way we think about this is not how many dots are happening that are like our statistic. That's p-value, is kind of looking at how many times our simulation was like our statistic. We're not going to do that. What we're going to do instead is we're going to say, how far is our statistic from the middle? So the standardized statistic, all this does is says, let's measure how far our stat is from the middle. But remember, this is the key point, why we do this. What is the middle? The middle was our assumed null value. So what was that middle? It was what we assumed was true. So what I'm really asking you when I'm saying do the standardized statistic is I'm saying measure for me how far your statistic away, so how far away your statistic is from that assumed value we're pretending it is. So in Buzz and Doris, what are we doing? We're saying, okay, I'm assuming 50%, right? I'm assuming they're getting it right 50% of the time. So the standardized statistic will help me measure how far away 15 out of 16 is from 50%. So remember, that was way out here, right? The 15 out of 16. And so that 15 out of 16 is 0.9375. So the standardized statistic is going to help us measure that. How do we measure it? Well, just figure out how far away they are. Subtract them. And then there's a mystery piece to this, which we'll talk about in another video.